All right, so in this video, we are continuing to derive the C6h character table. So this is a multi-part series, and where we've gotten up to this point is we've derived 6 different irreducible representations. And we know we have 12 classes, and the total number of dimensions we have has to equal 12 of our irreducible representations. Right now we have 2 plus 2 plus 2 plus 2 plus 1 plus 1 is 10. So we know we're actually 2 dimensions short. And so, you can, at this point, you can test some other functions. We've done, all of the simple quadratics. We haven't done z squared yet, but you can see z squared is not going to help you because that's just going to be the square of z, and that's going to get you ones across the board. So it's not going to help you derive a new function. And so the easiest thing at this point is probably to test new functions by using the orthogonality. So to come up with the irreducible representations using the orthogonality. And we have a lot of 2's here. We're just kind of guessing, but we're thinking that maybe we need some more 1's for our remaining 2. I think that's a good place to start. And so, and if you notice, the other thing to say here is that we can't really easily generate any new functions if you're from what we have. If you remember, multiplying anything by gamma 1 is just going to get itself. We already did the trick of multiplying other gammas that we derive from functions by the z function by gamma 2. So for example, we multiply gamma 3 by gamma 2 to get us gamma 4, xz, yz, starting from xy, multiplied by z. And we did the same thing for gamma 6. We multiplied gamma 5 by gamma 2. And so we're sort of out of that trick as well. And if you start multiplying, higher order things, you're going to get a 4 here. And most of the like gamma 5 by gamma 6, only the very highly symmetric character tables have irreducible representations with dimensions of 3 or 4 or 5. Those are very rare. So, that's going to get us some linear combination of irreducible representations, i.e. what's called an irreducible representation, if we were to multiply, for example, gamma 5 by gamma 6. So all signs are sort of pointing to us needing to find out something with a 1 here for our 7th irreducible representation. And we remember the principle of orthogonality, which states that the dot product, right, whatever this gamma 7 function is, that's going to have to be orthogonal with all the other functions, right? And so the dot product is going to have to be equal to 0. So for example, gamma 7 dotted with gamma 1 has to equal 0, and dotted with all the other ones. And remember, we normalize or adjust for these dot products by multiplying one of the vectors, each component of one of the vectors, by the number of symmetry operations in each class. We only have 1 symmetry operation in each of these classes, so this is just going to be a normal dot product. We're multiplying everything by 1 to adjust it, and that doesn't do anything, of course, multiplying by 1. But what you can see is that, in order for something to be orthogonal with the totally symmetric irreducible representation, gamma 1, since that's 1's across the board, and if we're going to have all 1's or negative 1's, that's what irreducible representations with dimensionality 1 are allowed to have. You are going to have half negative 1's and half 1's, meaning you're going to have 6 negative 1's and 6 positive 1's. You can see that's true for gamma 2. The first 6 classes have positive 1's, and the next 6 classes have negative 1's, because you're going to go 1 dot times 1. When you do the dot product, right, gamma 1 dotted with gamma 2 has to equal 0. 1 times 1 plus 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 1 times 1, that's all equal to 6. And then you do the same thing with the negatives. 1 times -1 is -1 plus another -1 plus 1 times -1, etc. That's going to get you -6, so the whole thing gets 0. So we can use this to kind of help us. We know that we're going to have 6 positive ones and 6 negative ones. So let's just write that down. It's sort of one of our constraints here. Of course, we're forced to have 1 positive 1 for the dimension, the character under identity. And then we can sort of think about, what about being orthogonal with, I don't know, gamma 6? Well, this is a positive 2. And so in order to be orthogonal with gamma 6, you're going to need either -1s or 1s here. You're going to need a way to make this all work. And so it's probably best to just test out different things. And so usually character tables end up being pretty symmetric. So there's a multidimensional space here. Why don't we just try something symmetric here where we do oscillating 1s and -1s and see if this works out. And maybe we'll get lucky. Oops, so that was a positive 1. This is 1 and -1 and positive 1. So that gives me 1, 2, 3, 4. Oops, I think I messed up here. There we go. So that gives us 1, 2, 3, 4, 5, 6 -1s. And so that's definitely going to work with gamma 1. Is that going to work with gamma 2, right? Dotted with gamma 2. Because all of these are 1s here, it makes sense that on this quadrant you would need 3 -1s and 3 positive 1s, which is what we have here, right? I have 1, 2, 3 on this half, I should say. And on this half of the vector, they're all -1s. So again, you're going to need 3 positive 1s and 3 -1s. So this symmetry sort of helps us out here, the symmetric nature of this thing. But then we just test with these other functions, and let's see, 2 times 1, let's say gamma 6 dotted with gamma 7. 2 times 1, 2. You're going to get, so if we write this out underneath, we're going to get a positive 2. I'm just multiplying these. 1, -1, so those cancel out. Then a -2, so that's cool. I'm at 0. And then -1, 1, -2, -1, 1, 2, 1, and -1. So that's 0. These cancel out. I'm at 0. These cancel out. I'm at 0. These cancel out. I'm at 0. And so then you can keep checking all these values here and make sure everything's orthogonal. If everything's orthogonal, you've actually found a new valid irreducible representation. So we do gamma 5 dotted with gamma 7. That's going to give us 2, 1, -1, -2. Well, that's all going to cancel out, add us up to 0. We got a -1, a 1 that cancels out. We got a 2, a 1, -1, and a -2 that's going to cancel out. And we got a -1 and a 1. So that all works out. So it looks like we're good. At this point, you're probably good, but it's good to keep testing here. Just to confirm, especially on these more complicated character tables. We just got to do gamma 4 and gamma 3. So let's do gamma 7 with gamma 4. We're going to get 1 times 2, 1 times -1, so -1, -1, 2, -1. Let's see, -1 and 2. So far, it looks like I'm at +2 overall. And then I'm going to get a -1. -1, I'm at 0, a -2, 1, and a 1. So that all cancels out. So gamma 4 is orthogonal to gamma 7. And then our last one we have to test is gamma 7 with gamma 3. 2, -1, -1, 2, -1, -1. That all cancels out. -2, 1, 1 cancels out. -2, 1, 1. That cancels out. And we already, by our principles before, kind of constrained the system such that it was going to be orthogonal with gamma 7 was going to be orthogonal with gamma 2 and gamma 1. So we don't know what functions transform as this, or if there's any that are easy but or simple, but we know that gamma 7 is a valid function at this point. So we're a valid irreducible representation, so we're happy. Now what's really nice is we can find gamma 8 just by using a principle which we used before. We can multiply this gamma 7 by our z vector, our gamma 2. If we do that, right, we know gamma, because if we multiply gamma 1, we're not going to get anything. If we do that, we end up getting negative, all these numbers are the same, the first 6, and then we make all these the negative of one another. So these are going to flip-flop. And so at this point, we are pretty close to finishing our derivation of the table. And this is actually gamma 8 there. I'm not sure why I put gamma 2, but what we can do now is actually assign Mulliken symbols. So we can erase these gammas, which were just these generic symbols for the vectors that we were using. And so let me go ahead and do that. And so now what we can do is we can use our Mulliken symbol rules, which I have a video that goes over Mulliken symbol rules. And all we do here is if we have a dimensionality of 1, a character of E, okay, the character under identity is 1, we're going to assign the Mulliken symbol as A or B. And if we're symmetric with respect to the principal rotation axis, which is C6, meaning we have a positive one, we're going to put an A. So this is going to be an A, this is going to be an A. And if we're anti-symmetric, meaning a negative one here, we're going to put a B, or we're going to put a B. And then if we are have a dimensionality of 2, we assign it a Mulliken symbol of E. And so moving on from here, we use the inversion operation to give it a U for ungerade if we are anti-symmetric, we have a negative value, or G if we are symmetric for gerade. These are German terms. This is just Mulliken symbol rules. So here we have, we call this AG because we're symmetric with respect to inversion. Here we're anti-symmetric, so we call it AU. And then we have BG and BU. And then lastly, we just have to do the same thing for the E. And so again, we just look here. We have a negative, so that's going to be a U. And here we have a positive for inversion, so that's going to be an EG. Here we have positive for inversion again, so it's going to be EG. And then here we have a negative for inversion, and so it's going to be EU. And so, of course, we don't want to have two Mulliken symbols that are both called EG or both called EU. And so at this point, we have to use the subscripts 1 and 2 to differentiate between them. And unfortunately, the Mulliken rules aren't really well defined at this point, so it gets a little arbitrary. And it turns out that people just call this vector the E1G, okay? This vector, the E1U, and this is E2G and an E2U. And if you look at this, there isn't really a nice way of saying why. But at some level, these are just arbitrary labels anyway, and as long as everybody's calling everything the same thing, it doesn't really matter. So at this point, the character table is mostly done. But there is a major problem, and this problem is actually going to take us quite a bit of time to solve. We've run into this problem before with the CN character tables and other CNH character tables I've done from C2H to C5H. C2H you don't run into this problem, but C3H, C4H, and C5H you do. And the problem is that you're violating character table. You're still violating two character table rules here. So although the dimensions, total dimensions of this equals 12, right? We have 1 plus 1 plus 2 plus 2 plus 2 plus 2 plus 1 plus 1, that's 12, which equals the number of classes. The sum of the squares of the diagonals doesn't equal 12, the order of the point group. So that's one of our character table rules, going back to the character table rules video. 1 squared plus 1 squared plus 2 squared plus 2 squared plus 2 squared plus 2 squared plus 1 squared plus 1 squared doesn't equal 1 plus 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 1 doesn't equal 12. Okay. And so that's a problem. The other problem with this is that the total number of irreducible representations doesn't equal 12, doesn't equal the number of classes. That's a simpler one to see. And instead, it only equals 1, 2, 3, 4, 5, 6, 7, 8. And so the way we're going to fix this is we're going to take all these E vectors, for example, the E1U, starting out, and we are going to split these up into two one-dimensional vectors, right? So, and the reason why we couldn't derive this organically without coming up with these aggregates, sort of these linear combinations of these two vectors that we're going to derive, is because there's no real functions that transform as these individual components. In fact, there's only complex functions or non-real functions that have real and imaginary parts. And so that's what we're going to have to do. And we're going to have to do that for E1U, E1G, E2G, and E2U. Once we do that, we'll end up in a situation where these are no longer valid. We cross these out, and we have, we've broken all these up, right? So we've broken, just for clarity, right? We've broken up the E1G, we've broken up the E2G, and we've broken up the E2U, and all of these old E's are going to be crossed out from our table. They are no longer valid. So then we'll have actually 12 ones in this column, and we'll have 12 irreducible representations equal to our 12 classes. We'll still call them by these Mulliken symbols, and we'll refer to them together. But, and then also 1 squared plus 1, 12 times is going to be equal to 12. So both those character rules will be valid. So it'll get into some heavy math with imaginary numbers, but that's where we'll go next.